Hey,
Hello, it's Quinn and
Hey.
AJ.
I can introduce myself.
Okay,
Thank you very
okay,
much,
okay.
Quinn.
Okay, so in this video, we're going to be talking about,
Asymptotic analysis.
also known as Big O notation. So, let's begin.
Okay. Wow, Quinn, it'd be really nice if you could start off with an example.
Oh, that's exactly what I'm about to do.
Oh, really?
Yep.
I doubt you have
Let's
one.
say you're doing some programming, right?
Okay.
And you like to name a variable
Okay.
is equal to, let's say, knife.
Okay. Yeah,
What
sounds good.
is the Big O notation of this?
Well,
What do you think?
I think it's big O of N.
Wrong. You're so wrong.
Wrong? Quinn, no, there's no way I'm wrong.
It's known as constant time.
What do you you think it's
People
constant
like to
time?
denote this as, I'm going to write this as a comment, guys. Big O of uno, one.
Why is it constant time, Quinn? Educate me.
Well,
The-
that is a great question, AJ. The answer is because this operation only has to happen once.
You mean the whole process only has to happen once?
Stop asking me questions, okay? Yes, the whole process, AJ.
Wow, Quinn,
So-
you're so smart. Do you go to Harvard?
Good one. So this is Big O of one. Now we're going to be talking about something that takes a little bit longer.
Oh,
Right. Yeah, and I'm going to write it out just for you. Okay? So that was Big O of one. Good job.
but I got
Now-
it wrong.
Let's do some math, some simple addition.
Okay.
You know what I do? Make it bigger. So you can see with your blind eyes. Let's have a little sum. And you know what? Let's use our favorite loop structure. And let's go from I to some number n. Okay?
Does it matter what N is?
Nope. It could be anything you like. And we're just going to increment some. Awesome, right? So what do you think the Big O of this is?
Is it big O of N, Quinn?
Oh, good job, AJ. Yup, it is. Why do you think it's the Big O of n?
Because the operation sum will be executed N amount of times.
This is great. Good job. Good job. Okay, so now we know how to recognize the Big O notation of two different types of complexity.
Yeah.
Let's go to
What
the
if-
next level.
What if if we have a problem besides big O of N, Quinn? Do you have an example for that?
What are you trying to do, AJ? What are you trying to do?
Maybe there's a logarithmic algorithm you could show me, Quinn.
Thanks for asking that, because that's exactly what I was going to show you. Let's say we take this linear, right, or Big O of n problem, and let's first copy and paste it. But instead of just adding one right here, you know
Yes.
what I'm instead going to do? I'm going to do something crazy. I'm going to just keep it simple. Do that. Now, what do you think this is going to be? You think this is
Wow.
going to be faster?
I still
Or
think
slower.
it will be big O of N, Quinn.
Really?
Yeah.
Why is that?
I'm willing to bet my girlfriend on it.
Your non-existent girlfriend on it. Okay.
Hey, don't talk about her like that.
Well, you might know. Okay. Oh, you might notice. First, I is going to be. Ooh, this is not good, actually. Let's start I at 1. My bad. Oops. So
Oh,
first I
that's
is
a
going to be
catch.
1. But after the first iteration, what is I going to be?
2.
Very good. Very good. So then what is it going to be? The next iteration.
4.
You're so smart, AJ. Do you notice it's doubling? Oh my god. It's increasing faster and faster. Faster and faster.
So what does that mean, Quinn?
It's a logarithm.
Wow. Gee willikers.
And it's written like this. Yeah. Don't forget the Batman. Great.
So, what other things are log n, Quinn?
Your mom is log n.
I thought a binary search tree was log
Yes,
n.
yes, that's also log n. And
Maybe operations like a hash tree?
oh, you know so much more than me. So that's enough about log n. I think we've covered quite a bit.
That sounds Gucci.
Very nice. Now I want to introduce you to something with a big O notation. And people usually like to write it like a big O, where it's in log n. And let's look at this little function we got right here. Boom. It's all good. It's okay. They can't tell. I'll pause it. Look what we got here. So this one's a little tricky, wouldn't you say, partner?
Well, Quinn, I'm glad I have you to explain it to me.
We sound so stupid.
Yes, you want it.
So we have the sum starting off with 0. But you'll notice these for loops are a little tricky, right? They're pretty tricky. This is similar to this. They're actually equivalent, okay? So that's the log in part. And in the second for loop, it's just a regular little for loop. And that's the in part, right? So here we got the log in, and here's the in. Boom, bada, bing. What do we get?
So I multiply them together since
Yeah.
they're interlocked in the same looping structure?
Oh, you said that perfectly. You said
Wow,
that perfectly.
Quinn.
What do you think's next? So let's just do a little quick recap. This video is starting to get long. We started with constant time, right? Then we moved on to linear time. Then we moved on to log n time. Then we moved on to something even slower, n times log n time.
You mean something
Even slower than
even slower?
n times log n time.
Wow. What could that be?
I don't know.
Could it be n factorial?
Oh, that's super slow. I was actually going to talk about n squared. Big O of n squared.
Oh, man.
So what do you think that is?
It's n squared.
N squared. What is big O of n?
Maybe if you just changed this loop and made it I plus plus, and so it had just had two loops going through n twice, it would be n times n.
No, you didn't. You smart little cookie. Ah. Ah. Boom. Big O of n.
Because I iterate through n once. For every iteration I go through I iterate through n. So I end up
Yeah?
iterating through n times. So what's n times n?
N squared.
Whoa. You're
Look at
such
you.
a good, you little dirty math major.
Stop. Okay. So we're getting slower. We hit n squared. We're pretty good. And let's just go on to something even slower than n squared. Even
Okay.
slower. So we just went over a big O of n squared. That's already very slow. But I want something even slower.
Okay. What could that be, Quinn?
Exponential. And here is a very simple example of an exponential function. The Fibonacci function, right? So let's say we're trying to find the Fibonacci of 10. When we first plug in 10, we're going to call it itself 2 more times. And that's going to call itself 2 more times. Right here and right here. And basically this is going to become an exponential.
So it kind of forms a tree, Quinn? Could you draw that out for me?
Definitely not going to draw that out, but yes, it forms a tree.
Lost it?
Yeah.
Let me show you guys an example here. So let's say I do run it with 10. Then I'm going to run it with 10. I'm going to check if it's less than or equal to 1. And then, but if it's not, I'm going to return Fibonacci n minus 2 and n minus 1. So I'm going to return Fibonacci n minus 2. What's 10 minus 2, Quinn?
8.
Yeah, you get it. Okay. And now what I'm going to do is I'm going to keep running those functions. So as you can see, I just went from one function call to 2 function calls of Fibonacci. And now I'm going to go to 6 and 7. And for this, 7 and 8. And I'll keep doing this till I get down to 1. And so that's how, and so as you can see, I go from 1 to 2 to 4. And I'd go to 8, and then I'd go to 16 as I went down, as the height of the tree increased.
How'd you pass 5th grade handwriting class? So, that was great, right? We started from constant time, now we're at exponential time.
Yeah. You know what I realized through this video? I hate you, Quinn.
Okay, that's a great place to stop. Thanks for watching, guys. This is AJ and Quinn signing off.